Okay. So ethers and epoxides, I said, first we want to know the structure for these molecules. The functional group for ether is a oxygen attached to 2 carbon. So if you have oxygen single bonded attached to carbon on the left, carbon on the right, the molecule is classified as ether. You have the functional group here. Basically, if you take the water molecule and you replace one of the hydrogens with the R group, you get alcohol. And if you take both of them out and you put R group, which is the alkyl group, you get ether. The hybridization for the oxygen is sp3 hybrid. Means the oxygen has 2 pairs of unshared electron. That makes this molecule to be polar molecule, where the oxygen side is a slightly negative and the alkyl side is a slightly positive. So the dipole moment or the polarity of the molecule is toward the oxygen. That makes the ether to be a polar compound in general. The bond angle, because it's sp3 hybrid, for sp3 hybrid, bond angle is expected to be 109, and that's expected. 109.5 is slightly higher than that, 110, because these groups are bulky. They are not like hydrogen, and they are kind of opening or pushing each other away, and makes this bond higher than the bond angle, higher than the 109, but it's very, very close to it. There is a dipole moment. That means the dipole moment of 1.3, it means that the molecule is polar, is not very highly polar, but it is polar. And it can dissolve the polar organic compounds in it as well. So we want to know about the structure of these molecules. We also want to know about the general physical properties for these compounds. What do you expect from physical property? When you talk about physical property, you're talking about boiling point, melting point. And what is responsible for boiling point? The change in boiling point for these compounds is the intermolecular forces. As we talked about alcohols, intermolecular forces affect the boiling point. If you compare the boiling point of water to alcohol to ether, so you're going from 100 degrees Celsius for water, for alcohol 78 degrees, and for dimethyl ether is minus 25, and this is very, very close. The two compounds, these two compounds, they have both same molar mass. So the only reason you have difference in the boiling point is because of the intermolecular forces. Water has 2 chance for hydrogen bonding per molecule because you have 2 OH bond. Alcohol has 1 OH bond, and ether has no chance for OH. So there is no hydrogen bonding. You would get only dipole-dipole interaction, and the dipole-dipole interaction is going to be not too high because the polarity of the molecule is just 1.3. Is not, the dipole moment for alcohol is higher than ether. And if you compare the ether to alkane because it's non-polar, is going to have even lower boiling point because you only have the London dispersion forces for the for alkane. Any questions about the trend, about like looking at these numbers? And you should be able to predict, if you are given like 5 different compounds, which one has higher boiling point and which one has lowest boiling point of the compound. Any questions? The hybridization, so it's talking about the hydrogen bonding. Ethers do not have chance for hydrogen bonding, and that's why they are going to have lower boiling point compared to alcohols. But since they are polar and they are, they can solvate, or they can dissolve polar organic molecules, but they don't dissolve in water. They are not polar enough to dissolve in water. Crown ethers, like 18 crown ethers. You have these, I think one of the questions was asking what's the name of this compound. So it's the 18 crown 6, the ether that you have here. It can solvate, or it can surround or stabilize cations, stabilize anions. With Grignard reagent, remember with the Grignard reagent, you always use ether as the solvent, because when the Grignard forms, there's an ionic compound, it needs to be stabilized. So they use like 18 crown ether in order to stabilize the Grignard reagent. So structure or hybridization for ether, you have sp3 hybrid. Polarity of this molecule, they are more polar than alkane, less polar than the alcohol. And the boiling point, it depends on the mass of the ether that you have. The lower the mass, the lower the boiling point. But that's like when you're comparing two ether. That's the intermolecular force is the same, but the mass is different. So some uses of the ether. Ether is a very good organic solvent. It can dissolve non-polar organic compounds, and it can also dissolve organic polar compounds. The polarity of the ether is not too high to dissolve in water. So after like physical property and the structure, we want to look at the naming, how to name these compounds. We have two types of naming. If it's a common name, you just say alkyl ether. Or if the two alkyl groups are exactly the same, you just say dialkyl ether. So like diethyl ether or ethyl ether, that's a common name for it, for this compound that you have here. For the, let me back this. So ethyl ether, that's is very common solvent in the lab, is used all the time. So in this case, you just say alkyl group and then the other alkyl group, and you can bring it, because this is common name, it's not IUPAC name. It's common name, and couple ways can be used. Either complexity. If it's a complexity, then you go with the least complex alkyl group, and then the more complex alkyl group. So it would be methyl T-butyl ether. Or if you go with the alphabetic order, you would use the T-butyl before the methyl. So it would be T-butyl methyl ether. There is a common name. For IUPAC name, you always go with the alphabetic order, but for common name, you could go with the complexity as well. If the groups are not the same, so you have ethyl group, methyl group, so you just say ethyl methyl ether. That's for common name. Any questions about the common name? Okay, when it comes to the IUPAC name, you are going to choose the longest carbon chain. And when you have the longest carbon chain, you take the oxygen with the smaller group as a branch, and you would consider that as a branch. So in this case, the longest carbon chain is 1, 2, 3. or 1, 2, 3. You cannot include oxygen in the carbon chain. And the smaller group, including the oxygen, is going to count as a branch. So it's like an alkoxy alkane. So basically you are naming your compound as the alkoxy alkane. In this example, you have methoxy and then cyclohexane. So methoxy, cyclohexane, alkoxy alkane. This example, you have a methoxy, and then you have your other branches in the main carbon chain. So you go with the branches first, other than the alkoxy branch. Other branches come first. So you have 2 methyl, and then you have 2 methoxy propane. So the groups that we have that as the branching in the in naming of ethers, methoxy, etoxy, isopropoxy. So as long as you know chapter 3 from organic chemistry, how to name organic molecules, this is the only new rule that is being added. You are naming part of the molecule as a branch, and that is not just the alkyl group, is the alkyl attached to the oxygen, and you would name it in general like alkoxy. If you have 1 carbon, it's going to be methoxy. With 2 carbon is etoxy. For like, if it looks like isopropyl carrying oxygen would be isopropoxy, and then sec-butoxy. Cyclic ethers, if it's just the 3-member ring, they are known as oxyran. Basically, you have 2 carbon with the oxygen, is a 3-member ring. So just know and be familiar with that. So oxane, oxane, and basically these 2. Make sure that you know the structure for those 2. Oxyran and then oxanes, which is the 6-membered ring with including the oxygen. It looks like cyclohexane, but one is oxygen. One group is oxygen. Okay, and then if you have like a dioxane, for the dioxane is a 6-membered ring with 2 oxygen. With 1 oxygen would be oxane, with 2 oxygen would be dioxane. Just these 3, please know the structure or recognize the structure. Any questions? I don't want to just read this slide to you. I want to make sure that you at least know the point of this slide is nomenclature for cyclic ethers. And the cyclic ethers, just like the regular acyclic ethers, you have oxygen attached to 2 carbon. That's the functional group for the ether. A general name for this molecule, just like you have general name for benzene. So this is like an oxane. If you have 2 oxygen, is a dioxane. If you have questions, please use the chat. So you can, use the chat to give me to write any questions that you might have. Okay. Just want to make sure that I can answer your questions while you are listening. Please also take note as much as you can. Okay, so structure or formula for ethers. Physical property, which is boiling point solubility, uses of the ethers, how to name these compounds, and then it would be how to prepare these compounds. Okay. So the naming for when you have like an oxyran part of the ether molecule. It can be named from the molecule that has been basically prepared. So in order to prepare this ether or this oxyran, you start with cyclohexene, and then you oxidize this. When you oxidize hexene, you are using proxy benzoic acid. What is proxy benzoic acid? So if you have the benzoic acid that looks like this molecule, COOH, a proxy benzoic acid is going to look like just like a hydrogen peroxide. You have two oxygen, you have a proxy group. This is very unstable. It's very good oxidizing agent, and it can oxidize carbon-carbon double bond. And when it does oxidize, basically one of these hydrogens is going to form a ring with the carbon-carbon double bond, and you are going to make the oxyran here. Is addition of is oxidation, but formation of the oxyran, basically. So, or you're making like an epoxide. So they are known as oxyran or epoxide. When you are naming, you can go with the origin. You just say that this is a cyclohexene, but has been oxidized. So if you say cyclohexene oxide, that's one way of naming the epoxy or naming the oxidants. You could also use the name this as just oxidant. So you are going to start numbering the ring first. So to number the ring, you start with the oxygen 1, and then you move to the side that you can move with the side with the alphabetic order. So you are going to have oxygen 1, and then you have carbon 2 and carbon 3, carbon 2, and you have your carbon 3. Because you have two substituents, and then you are going to look for alphabetic order. So you have an ethyl group. So instead of going 1, 2, 3, you would go 1, 2. You would assign the 2 to the carbon that carries the ethyl group rather than the methyl group. Then you can name it. These groups are an opposite side. When you have a cyclic system, you look for the groups if they are on the same side or if they are on the opposite side. If they are on the opposite side, you would use trans. So the name of the main part of this molecule is oxyran. Basically, you have the oxyran, and you have some groups attached to it. So you name the branches first and then say oxyran. That's another method of naming. So you could name it as oxyran, or you could name it from the original compound that has been prepared as the cyclohexene oxide, as an example. Or if you have an alkene, let's say you have 2-butene and then say oxide. So it would that would be another naming for this molecule. The mass spectroscopy and IR spectroscopy has not been covered yet, because it's in the book. It comes from chapter 12 and chapter 13 for NMR, IR, and mass spec. That's why it's part of this chapter, but I am not going to cover the IR or NMR of the ethers at this point, because we need to, and the mass spec, because we need to first cover those. That's why I said I might skip some of these slides, and that's one of them. That means at the same time that you are not responsible for IR and NMR until your exam 2. Okay, synthesizing ethers. One method to synthesize ethers is Williamson synthesis of ethers. We talked about this at the end of chapter 11. You start with the alcohol, and with the alcohol, if you start to say with the example of CH3CH2OH, you mix that, you are going to make it react with a strong base, either sodium or potassium, and that will change to alkoxide. Basically, this is a strong base, is going to remove a hydrogen, so it's going to change to CH2O minus. You have a strong base, at the same time a strong nucleophile, then it can react with alkyl halide. So you bring your alkoxide, make it react with alkyl halide. Alkyl halide, and this is going to be substitution reaction. You have your nucleophile and you have your leaving group. So the nucleophile, if it's for an SN2 reaction, a nucleophile is going to attack and the leaving group is going to leave. So a new bond between oxygen and carbon is going to form. When you make this molecule, one part of the molecule is coming from alkyl halide and the other part of the molecule is coming from alkoxide. So the overall molecule, it carries the ether functional group and you have synthesized ether. The method is called Williamson synthesis of ether. So you could use sodium, potassium, or sodium hydride for the as a strong base to remove the hydrogen. Other examples you have here is the cyclohexanol. Basically, if you want to go do like a retrosynthesis, what does it mean, retrosynthesis? This molecule, ether, is coming from two different reactants. One is alcohol and the other one is alkyl halide. So we can cut the molecule in half like this way. This side of the molecule comes from alcohol. This side should come from alkyl halide. I hope that you you can follow this. So the other choice would be if you cut on this side. So if it's A, you would get, for A, you would get the cyclohexanol. For B, you would get methanol. I'm sorry, ethanol, CH3, CH2OH you start with. So your starting material, it depends on where the cut is. When it's like a simple, there's really no unique structure, then you have like two choices. But if you have, for this structure, can you tell me which one is the better choice, A or B? I'm going to wait for a response before I move on. Can you tell me, and what's the step of this reaction? Because I already explained up here, what's the step of this reaction can indicate, or can, the effect of A or B is going to be more significant. Which one should we choose, A or B? Basically, you have two choices: to use A as cyclohexanol as the alcohol, and then you would use the CH3, CH2Br as the alkyl halide, or you would use ethanol plus, let's say, cyclohexyl bromide. Which one is the better choice? A or B? And please respond. Even if it's not B, thank you, or A, let's see. B, okay, and can you justify why B is better? I'm not saying it's right or wrong. What are you looking for to make the reaction faster? This is the SN2 type reaction. So if it's the SN2 type reaction, that would be your hint. If it's SN2 type reaction, what makes the SN2 type reaction faster? What's the point of difference here? The point of difference is, in this case, you would have a primary alkyl halide. For choice B, you have a secondary alkyl halide. Would that make any difference in your answer? Bromine is good leaving group, and we do have bromine. Thank you so much for your responses. Bromine is a good leaving group, and since we have bromine on both cases, I don't know how I can make this part. Okay, it worked. Okay, you have bromine as the leaving group in choice A, and you have bromine as leaving group in choice B. So that's not the point of difference. So we are looking for point of difference. The point of difference for A, your alkyl halide is a primary alkyl halide, and for B, alkyl halide is a secondary alkyl halide. So because it's the SN2 reaction, you are looking for which one? Primary or secondary? Okay. SN, did I say, for what about SN2? For SN2, it would be primary. For SN1 would be secondary. So for SN2, primary is greater than secondary, greater than tertiary. For SN1 is the opposite. Tertiary is greater than secondary, greater than primary. In Williamson synthesis reaction is going to go through SN2 attack or SN2 reaction. And for that reason, we want our alkyl halide to be primary. That's why when you are trying to synthesize, especially with the retrosynthesis, you want to make sure that your alkyl halide is a primary alkyl halide, not a secondary, when there is a choice. Okay. In this case, like this example, what should be, well, this molecule, it can be cut through carbon oxygen, like methyl and oxygen. If methyl and oxygen is cut, and if I call this one A, I'm going to have CH3Br or CH3I as the alkyl halide. And plus, the other side of the molecule would be the alcohol. But since the other side of the molecule, that is the alcohol, after losing the hydrogen is going to be very strong nucleophile, alkoxide, it doesn't matter. So your nucleophile is strong anyway, and this is a primary alkyl halide, and this attack is going to be faster than the other choice. What is the other choice? The other choice, so if this is A, the other choice, I'm going to use a different color here. The other choice is going to be cutting through here for B. And for B, you are going to have a CH3O minus, that's your alkoxide, plus the other side of the molecule that is going to be Br. Since you have like a secondary alkyl halide here, this can take place, but because you have a good leaving group here, this reaction can take place, but the first reaction or A reaction is going to be much faster. So A is better than B. So you have two way to, when you are asked question for these like chemical reactions, there you have three types of questions. One type of questions, be just ready for that type of questions. One, reactant is given to you, okay? Reactant is given to you, reagent is given to you, and then they're asking what's the product. A second type of question, reactant and product is given to you both, and you are asked for the reagent, what type of reagent you need to use. Other type of reaction, the product is given to you, and the name of the reaction is given to you, Williamson synthesis, and they say, okay, prepare this ether using Williamson synthesis method. Then you have to know that, okay, you have two choices for the retro. We know that in Williamson synthesis reaction, we have alkoxide, we have alkyl halide. So one side of the molecule is coming from alkyl halide, the other side is coming from alcohol or the alkoxide. And which side should I choose? Because it's the SN2 type reaction, my alkyl halide should be primary alkyl halide. Questions? Okay. When you have phenol, this is the phenol. When you have phenol, phenol is a stronger base compared to alcohol. So for phenol, you don't have to use sodium or potassium or sodium hydride. you can use just the base, like a normal sodium hydroxide or potassium hydroxide. So when you have phenol, you have less problem. And if you have a product, you have an ether that one side of the molecule is O and the other side is CC, for example, and or any combination, you want to make sure that in this case, you take the phenoxide as your phenoxide as the alcohol. So you start with the phenol. So if this is different from the cyclohexane, this is a benzene ring attached to oxygen. So this part is preferred. So whenever you do retrosynthesis, you are going to break the bond between the oxygen and the other alkyl group. So this is like a priority. Oxygen goes with the benzene ring because it's more stable. This alcohol is even more acidic. 2-nitrophenol is better than phenol because electron withdrawing group is going to increase the acidity. So 2-nitrophenol has a nitro group, which is nitronium ion. Nitronium ion is NO2+, a strongly electron withdrawing group. It pulls electron from benzene ring, and it makes this is like a fluoride that is attached to benzene ring, is going to make this phenol a stronger acid. And if it's a stronger acid, definitely you can use just sodium hydroxide. You don't have to use sodium or potassium. Okay? And the alkyl halide that you have is also primary. The reaction would go through fast because you have a good nucleophile, very easy to form because removing of hydrogen is very easy. You have your peroxide and then you have your alkyl halide, and the reaction would go through. In this reaction, when you have the a bulky, because it's an SN2 type reaction, you see when you have a tertiary alkyl halide, this reaction is not favored. Okay? It's not a favored reaction because of the tertiary alkyl halide that you have. Instead of the substitution reaction, in that case, you are going to get like this would act as a strong base and it will go through elimination type reaction. But if the alkyl halide is the primary alkyl halide, and because you have an SN2 reaction, the product is going to be ether. So that's why you're in a SN2 type reaction, you want to make sure that your alkyl halide is a primary alkyl halide. Preparation of ethers, you can do, you remember the reaction for oxymercuration-demercuration from chapter 10? In the, for the preparation of ether, you would do alkoxymercuration-demercuration. So alkoxymercuration-demercuration, the difference for that between oxymercuration and demercuration is that in oxymercuration-demercuration, in this step, you had water instead of alcohol, but here you have alcohol. That's the only difference. So what is happening here, you do the alkoxymercuration first. So this side of the molecule, the OAC, HgOAC is going to be your nucleophile. I'm sorry, your strong electrophile, and is going to attack the pi bond. The pi bond is going to form bond with this mercury here. Mercury is a mercury 2 acetate, but it does ionize to acetate ion and mercury. So you have OAC, HgOAC with the plus charge plus the OAC minus. This is just the acetate ion. Okay, so after it ionizes, you have this acting as a strong electrophile here. So it's an electrophile that is going to be attacked by the pi bond, and then this side of the molecule is going to be positive. So when you bring electrophile to one carbon, the pi bond, because it doesn't bring any electrons, this pi bond is going to be consumed to form the bond. And if the pi bond is coming to form the bond with the electrophile, the other carbon will take the plus charge. So when the other carbon takes the plus charge, then your alcohol in this case is acting as a nucleophile, and the nucleophile with the nucleophilic attack is going to form bond with the carbocation that form. This is a two-step reaction. It doesn't give you the mechanism for reaction because the mechanism for oxymercuration and demercuration was covered in detail in chapter 8 for the oxymercuration, like it's just the addition reaction. The only difference is that instead of the water here, you have alcohol. So you get the product of the oxymercuration, and then in the next step, you do demercuration. So this is like two-step reaction. You want to make sure you separate your reagent by number because there is two-step reaction. In demercuration, reduction takes place. Basically, a hydride ion is going to replace this whole complex here, and you end up with the oxygen attached to two carbon bond, which is ether. With this example that we have here, that I just want to show you what the net result is. The net result of oxymercuration, demercuration, because for multiple choice questions, you don't really need all the intermediates. You often need the final product, is addition of or indirect addition of alcohol to carbon-carbon double bond. The addition, in any time you do oxymercuration, demercuration or alkoxymercuration-Demercuration, the product is going to be Markovnikov product. And what does Markovnikov product means? It means that the carbon with the more number of hydrogen is going to gain the hydrogen. The other carbon is going to gain the rest of the molecule. So it's basically addition of alcohol. And what is addition of alcohol? Addition of alcohol, just like addition of water, I always say these are very simple things. When you say add H2O, it means add H and add OH, okay? When you are adding alcohol, when you add CH3OH, what it means basically, it means that you add H and add CH3O. So you are adding alcohol to this carbon-carbon double bond. Hydrogen will be added to one carbon, and the CH3O will be added to the other carbon. Because the addition, based on the catalyst that you are using, is a Markovnikov addition, hydrogen will add to the CH2, and CH3O would add to the carbon, the second carbon, which is the CH. And that is your final product as ether. Basically, the net result here is formation of the ether when you have the functional group of ether. So to the alkene, you're adding alcohol, but it's an indirect addition via alkoxymercuration-Demercuration, and the product is going to be Markovnikov product. The second method, we talked about the reactions of the alcohol, like bimolecular dehydration. If you control the temperature at 140, you would get bimolecular. That means that two molecules of alcohol would lose one water, hydrogen from one alcohol, OH from another molecule of alcohol, and the ether would be the final product. The key is this, or the cutoff is the temperature. It has to be like 140 degree rather than 180, because if it's 180 is going to give you there's a typo here. This is 180, it must be 180 degree. If it's 180 degree, it's going to be unimolecular dehydration, and ether is not going to form with 180 degrees Celsius temperature. Questions about preparation of ether? No questions for preparation of ethers. I'm just waiting for a response to make sure that you don't have questions. I'm using the other screen for your chat. Questions? No questions? No questions. Okay. Now, we are moving to a next concept, which is reactions of ethers. Now, so far, we talked about naming ethers, physical property for ethers, the structure of the ether functional group. We talked about preparation of ethers, and then next step is reactions of ethers. Now, if you have ether, what can you do with ether? What type of reaction ether would go through? There's another aspect also for organic 2, which I don't have it for organic 1, is the spectroscopy. We didn't talk about the spectroscopy yet because we have not covered the spectroscopy chapter, but after we cover spectroscopy chapter for every family of organic molecule, we also have to look at what are the major functional group and what would be the location in the IR spectrum or the indication like in the pattern or fragmentation pattern in mass spec or NMR. One of the reactions of ether is like the cleavage of the ether. That means you are going to cut the molecule of ether into 2 molecules. And in order to do that, you have to use a catalyst, first of all. You can do the reaction by heating with the HBr and the HI, hydrogen bromide and hydrogen iodide. The first step, so the HX that you are using here as HBr or HI, the H plus is going to use as a catalyst, is going to protonate the oxygen. When oxygen is protonated, now you see that this molecule is going to look like alcohol, okay? RO or alkoxide, like this example, methoxide, it's a very strong base, and because it's a strong base, is not a good leaving group. But if you add proton to it, if you protonate this, you change this to CH3OH, then it's going to become alcohol. Alcohol is very stable and it becomes very good leaving group. Just like when you had hydroxide ion, and you said that hydroxy group or hydroxyl ion is not a good leaving group, OH is not good leaving group, but when you protonate that, it would change to OH2, and then H2O can leave. The plus charge can stay, but H2O, which is water molecule, can leave. Same idea here. H plus is going to protonate the ether first, and then we have the alcohol is going to form, and alcohol is going to be good leaving group. Now, the choice of when it's symmetrical, there's basically you have either side can leave. So when the nucleophile, so H protonates, and then halide comes in as the nucleophile. When the nucleophile comes in, leaving group would leave. So when the nucleophile comes in this case, the way that is drawn, when the nucleophile comes in, you have is going to attack this R group, and then the alcohol is going to leave from the other side. It's like kind of the back attack, because either side is going to be alcohol. Alcohol is going to act as the leaving group. One side of the molecule would leave as alcohol, the other side of the molecule would change to alkyl halide. This is basically the opposite reaction to the opposite reaction to Williamson synthesis. In Williamson synthesis, you start with the alcohol and alkyl halide, you end up with ether. And if you do cleavage using the HBr or HI, you can actually change that to alkyl halide and then alcohol as well. Questions? Okay. When you have the alcohol in presence of this, this reaction can continue. Basically, it can protonate now the hydrogen. When it does protonate the hydrogen, H2O can leave if it gets protonated, and then the halide is going to replace the OH group. So that's the end result. You could have two alkyl halides when you're using HBr. As long as you know that at least the first step. The first step is more important, and that's the part that is basically, you would see that in the exam often. The second step, you don't see it often. Okay, a unique situation here. When you have benzene ring, which way is going, which side would give you the alcohol? Like you have two choices here, right? The two choices that you have, again, would be choice A, where you get this side as alcohol, as the alkyl halide, and the other side as alcohol, or you have your choice B, and with the choice B, you would get the left side as the aryl halide in this case, and the right side as the alkyl halide. Remember, I said when you have benzene ring, it is very unique, and the product is going to be phenol. So when there is a chance for formation of phenol, make sure that phenol is forming. It's going to be a lot more stable, and it's going to be a much better leaving group in this case. So then we have the alkyl halide for the other side that is forming. And when this reaction takes place, you cannot replace this with another Br. It kind of stops here because phenol is very stable. Okay. You know, you're all allowed to ask questions, right? In case if you have any questions, you could ask, you can stop me to ask your questions. Okay. Some of the reactions of ether is called autooxidation. I'm sure in the lab you have heard about do not heat up the ether, or when you have leftover of ether. When you look at the safety video, it says that you cannot leave the ether in the lab. It has to stay in the fridge, and especially if it's like halfway empty. So when it's halfway empty, that means you have air on the space head that you have. More air means more oxygen is available. And then when you have the more oxygen available in the container, and the temperature is not very cold, basically you don't keep the ether in the refrigerator, is going to auto-oxidate. And when it does auto-oxidate, it's going to change to epoxide. So when the peroxide is explosive compound, it's like this. These are very highly explosive compounds. So you have the hydroperoxide, and then you have the peroxide, the product of auto-oxidation of ether. So peroxide, this is the hydrogen peroxide. The meaning of the peroxide is just this carbon, oxygen single bond peroxide. And then when you have dialkyl peroxide, you have the, instead of the hydrogens, you have the R groups, highly explosive compound. You try to avoid it in the lab, and that's why you cannot keep the container outside of the fridge, and they must be kept under very cold temperature. They must be stored like that. Sulfides, just like ethers, because oxygen, you have the oxygen periodic table, then you have sulfur. So it can form also single bonded to 2 carbon. And when you see this, these are known as the sulfides. And then just like the SH, if you have a SH, you have like thiol. So naming of these is like, just like naming ethers, you would say sulfide. So alkyl, alkyl, sulfide. So you have phenyl methyl sulfide, or you have dimethyl sulfide, dimethyl sulfide. You have dimethyl sulfoxide. Okay. Dimethyl sulfide is a good solvent. They use it in the ozonolysis because after the reaction takes place, sulfur is going to be oxidized and it changes to dimethyl sulfoxide. Dimethyl sulfoxide, basically DMSO, is a aprotic, polar aprotic solvent on its own that can be used for the SN2 type reactions. Okay, dimethyl sulfoxide, and this is a dimethyl sulfide. So basically, alkyl alkyl sulfide, and it's one of those topics that is not my favorite really, but I just want you to look at the pattern. Just like alcohol is known as the thiol, and then you have the instead of the ether with the sulfide ethers, they are known as the sulfides. To prepare them, very similar to preparation of the ethers, and you would use thiol instead of the alcohol, and thiol would look like this. Thiol looks like this: CH3, CH2SH. This is more acidic than the OH. You can remove this using a base. And then you have the thiolate. The thiolate acts as a nucleophile. And with the alkyl halide, nucleophilic attack, a leaving group is leaving, you can get the sulfide, preparation of the sulfide. The reaction of this reaction is a SN2 type reaction. Because it's SN2 type reaction, you want to make sure that the alkyl halide you are using is a primary alkyl halide. Whenever possible, use the primary alkyl halide. And because it's the SN2 type reaction, see that the stereochemistry, if you start your reactant is a R compound, the product is going to be S. This is known as the Walden inversion, and that is the inversion of the stereochemistry, or the configuration is changing, is going to be inverted from R to S. In a SN2 type reaction, the attack of the bulky group is from opposite side where the leaving group is leaving. Basically, the order of the priority is changing. Priority, if it was moving from the most or highest priority to lowest priority, if it was clockwise, now it's going to be counter clockwise. some reactions that you want to, you want to pay attention to. Formation of like epoxide. This is actually one of the questions you have in the quiz also. So you're paying attention, is also in the homework assignment. So when you have, remember formation of the halohydrin. Halohydrin is like when you have carbon double bond and you are adding both water. If you add water to carbon double bond, so let's put it this way. If you add water, H2O, in presence of, catalyst, which is acid, you would get alcohol, OH. Now, if you add Cl2, you would get chlorine attached to it. But if you mix these two, you add both of them, you add water and you add Cl2 to carbon double bond, you are going to end up with halohydrin. In this case is a chlorohydrin. That means one carbon would take OH and the other carbon would take halogen. If you have halohydrin, if you add base to halohydrin, so the next step, this is like a second step of the reaction. In the next step, if you add base to it, so you are adding like sodium hydroxide, what's going to happen in the basic solution, this is going to deprotonate. So the base is going to remove hydrogen from the OH. You have the negative charge, and that negative charge in the oxygen is going to act as a strong nucleophile. When you have a strong nucleophile, that strong nucleophile now it can attack the nucleus. So it's thinking, even though it's in the same molecule, but it's thinking as an alkyl halide. So this can form, oxygen can form bond with the carbon and the chlorine can leave. So basically you are going to get like epoxide. So let's say you have alkene, and let me just, give you a scenario. So let's say you have alkene, CC double bond, and then is asking you this. You're adding H2O, you're adding Cl2 or Br2, either one, or Br2, and then you're adding sodium hydroxide. What would be the final product? So the final product of these two, when you have two-step reaction, they are either like separated by numbers or by two separate arrows, and the final product for that is going to be epoxide. Now, if you were going to look for the mechanism for the reaction, so after you have the halohydrin, you have to say that this OH is going to be protonated, or the H plus is going to be abstracted by the base or deprotonated. You have a strong nucleophile and nucleophilic attack, leaving out the leaving group, and new bonds going to form between oxygen and carbon. So you are going to get epoxide formed. Now, if you have epoxide, which is an ether, it's called actually like opening of the ring, epoxide opening in a basic solution. It can be different from the acidic solution, but what is happening in a basic solution, in a presence of the hydroxide as a base, is going to have a nucleophilic attack. So this is acting as a nucleophile. And if it's acting as a nucleophile, is going to attack a carbon with positive charge. The other choice would be to attack the oxygen. Which one would be better candidate? A carbon here with some positive charge, and what gives the carbon positive charge is the oxygen, because oxygen has high electronegativity, because it's attached to this carbon is going to give positive charge. This carbon is also positive charge. So when you bring the nucleophile, it's going to attack this. And since carbon already has 4 bonds, so if you count the bonds for this carbon already here, you have 4 bonds already. When the new bond comes in, so you have 1, 2, 3, and 4. 4 bonds already. When the new bond comes in, that's the 5th bond that is forming and is not good for the carbon. It makes the carbon very unstable. And since it's unstable, the weakest bond is going to break. And I'm sure you will all agree that a triangle is not very stable because of the angle strain that is there is not stable. So if this bond is broken, then basically you're removing that angle strain from the ring, and that makes the oxygen better candidate to leave rather than the hydrogen to leave or the carbon would leave. Hydrogen cannot leave and the carbon cannot leave. So the best choice here would be to oxygen to leave. And when oxygen leaves, because hydroxide is negative charge, when oxygen leaves, it's going to take the pair of electron and you get negative charge there on the oxygen. So you change that to alkoxide. And when you protonate, or when it's protonated using water, it's going to form diol. So if you hydrate or opening hydrolysis of oxidants or epoxide is going to give you a vicinal diol. So you get a diol, formation of a diol. The addition is anti-addition or anti-addition. It means that the OHs are not added from the same side, because the OH always, the nucleophile always come from the opposite side than the leaving group. And since this is already established, the bond is already established, is going to go to the opposite side, and then the addition is going to be anti-addition, and the molecule is a trans diol. Any questions? Okay. Which one is going to open faster or better with the hydrolysis or addition of water? Which one would change better to alcohol or gain the OH bond? The epoxide, because it has higher energy already, is more ready to break or open this ring, and is going to take less time or is a faster reaction. The activation energy for this is much lower compared to the alcohol or from the acyclic ether. So that's basically what is comparing. It's going to be faster. You have any questions for me? Please let me know if you have any questions. So what is going to happen when you bring the etoxide in ethanol, sodium etoxide in ethanol to this epoxide molecule or oxidant? Basically is a ring opening again. When it's ring opening, you bring a base. This is a base or nucleophile is going to attack the ring, and which side of the ring is going to be better candidate for this, A or B? Which one carries more positive charge, basically, because this is negative charge and is looking for positive charge. Carbon A has more positive charge than carbon B. And the reason for that is very good. The reason for that is that carbon B is supported by this methyl group and is more stable. So plus charge is going to be found around carbon A more often. So carbon A is more positive. As a result, is going to be better candidate for this base to attack. So the base is going to attack the least substituted carbon. The difference between A and B, if you're looking at it, is that A is least substituted carbon and B is more substituted carbon. So when you bring a base, the base is going to attack the least substituted carbon. And you see the addition is going to take place in this area. And the carbon that is least substituted or has more hydrogen. If you bring in acid first, then it's going to be opposite. When you bring acid, you are going to protonate the oxygen. And then when you protonate the oxygen, you have a plus charge that is going to move toward highly substituted carbon. And as a result, the addition is going to happen on the highly substituted. That's another good question, and like for the exam, for the quiz, when you have ring opening in a basic solution, the attack or the addition, when we say ring opening, you have oxidant or epoxide, okay? The base is going to, in a basic solution, or if the base is a base-catalyzed, the addition is going to happen at the least substituted carbon, but if it's an acidic solution, it's going to be on the most substituted carbon. Just keep that in mind as well. Okay, you can review this on your own. Don't know what happens if you add, that's another quiz question. And the quiz questions that you have, it might, it's going to be slightly different from, your friends. So addition of organometallic reagent, that would be alkyl lithium, or it could be Grignard reagent. Where would the attack take place? On the most substituted or the least substituted? So in this case, with the same justification, when the organometallic compound comes in, is going to form bond with the carbon that is least substituted because it's looking for a carbon with a positive charge. So you have the more positive charge on this carbon. So the R is going to form bond with the least substituted carbon. Same thing. If it's symmetrical, then it's not going to make a difference. This oxidant is a symmetrical one. So when you bring the Grignard reagent, you actually can get primary alcohol with addition of 2 carbon. In chapter 10, you learn about addition of Grignard to formaldehyde. It would give you primary alcohol with addition of 1 carbon. When you have oxidant, it will actually form primary alcohol with addition of 2 carbon. So if you were going to do retrosynthesis, again, this is a good method to remember that addition of Grignard to oxidant can give you primary alcohol as well. If it's substituted oxidant, like the top example here, you get secondary. If it's di-substituted, you can get tertiary. What is a di-substituted oxidant? Is like you have this, you have a CH3 here and a CH3 here. This is a di-substitute. Now to this, if you're adding a Grignard reagent, MgBr. You have the uniqueness about the Grignard reagent is that carbon takes a negative charge. Carbon usually is a positively charged unless it's facing a metal. So in Grignard reagent, carbon can act as a nucleophile. And since it can act as a nucleophile, it can attack any carbon that has positive charge. So in this case, you have the positive charge here. So it can go to like a, sorry. We said that it would go to the least substituted carbon. So it's going to attack this. And then oxygen will break over the tertiary carbon. And as a result, you will have a tertiary alcohol. Let me erase this so it doesn't get confusing. So Grignard would go to the least substituted carbon. And if it's symmetrical, like this oxidant down here, it doesn't matter which one, you will get primary alcohol. If it's substituted, you could get a secondary alcohol or tertiary alcohol. Questions? No questions? Okay. We have alkyl lithium, which is very similar to the, sorry. Alkyl lithium, which is very similar to Grignard reagent. Carbon here is negative charge because lithium is positive charge. This is a nucleophile. And when you have the nucleophile, it's going to attack the least substituted carbon, and the OH will break over the other carbon. So you get alcohol in this case. You're adding Grignard reagent to, again, another oxidant is highly substituted here, and Grignard is going to attack, okay? Grignard is going to attack least substituted carbon, and the OH will break over the tertiary carbon in this case, and you get tertiary alcohol. Questions?